Hi, hopefully no more phone calls. 12.2, Introduction to Vectors. Here we go. So you have your note packet out. You can pause it. You can speed me up. You can slow me down, whatever you need to do. You can break it into 57 little chunks. Whatever you want to do sounds good to me. I'm going to try to do it in one shot because I don't know how to use editing software to hem it together. So hopefully I won't get any calls. Oh, I did get it going back forward. I had it backwards there for a while. And so 12.2. So this is the introduction to vectors. And I'm moving my camera a little, actually side to side. I think it's actually not too bad. Okay, so we need vectors because it is difficult, for example, to describe motion in 3 dimensions or even in 2 dimensions without vectors. Just speed or just direction is not enough to tell us where we are going. If I said I was going 70 miles an hour for 1 hour, you don't know where I went. But if I tell you that I was going north or if I was going east or west, then you have some idea. So that's the idea in that a direction, that vector gives you also direction along with information such as speed. So vectors have both magnitude and direction. Magnitude can be given by speed or force and is the length of the vector. Direction can be mapped on the XY coordinate system or the XYZ coordinate system, so in 2D or 3D, and can be given as an angle from an axis. The vector with the initial point A, and that's called the tell, and the terminal point P, that's called the head, can be denoted A to B. And so there's the little tell, and this is like a half, the little notation is like a little half arrow there to mean vector, or it can be called V, and then you would put the V with a little line with the half on it. When I draw one, it'll be a little tiny bit bigger, and that'll be lovely. So this one here is telling us if you have a point A, -3,5, and a point B, -1, 2, so we're going in 2 dimensions just to get the idea, then draw this vector. And so I'm going to come here and I'm going to get this ordered pair, -3, 1, 2, 3, up 5, 1, 2, 3, 4, 5. So that's A right there. And then I want to get B on here, and that's -1, 2, 1, 2. There's B. And then we're wanting to draw the vector that goes from A to B. So start here at A, that's the tell. And I'm going to go to B, that's called the head. And then you would use an arrow here to show that I was going in that direction. If you want to find the magnitude, what is going on? Oh, I had that up in the window is what I had. That's going to drive me crazy the entire time. Sorry. But you guys have to move up in the window. And then I use the block. You can't see what I'm moving, but if you saw my setup here at my house, you would say, and you're using yoga blocks to block up your computer monitor. And the answer is, I am. It's true. And so find the magnitude, A to B, and what the magnitude is the length of this vector. And you have the choice to use the Pythagorean theorem if you want, and that would work out really well to find the length of this vector. Or you could use the distance formula, your choice on that. I'm just going to use the Pythagorean theorem just to show you right here. So I have here is 1, 2, 3, so that's a side of 3. And right here, going this way, can you see where I'm drawing on there? Is a side, a length of 2. And so using the Pythagorean theorem, I want to find that distance, which is the magnitude of the vector. I forgot to tell you that that's the notation that they use in our book for magnitude of vector. Some books use double. Some books use this for the magnitude of the vector, how long the vector is. They use like double absolute value. Our book just used single, so I'm just following our book. And so if I want to find this, then the magnitude, which is the length, this thing here, squared, right? Pythagorean theorem. Would you be happier if I called that C and then said that C equals, so here, C squared equals 3 squared plus 2 squared, which is 9 plus 4, which is 13. So c squared equals 13. Thus, c equals the square root of 13. And what we were finding when we found c was the magnitude. So that magnitude AB right here is equal to the square root of 13. Then they're asking me to draw another vector on here, the one that goes from 5, 1. So over 5, 1, 2, 3, 4, 5, up 1. And D is 7, so 7's all the way here and down 2. And this was C, this was D, and we wanted to go from C to D, so C to D. That's the tail, that's the head. And I hope that you're noticing that, hey, that vector is also 3, 2, because the first thing they asked me right here is to find the magnitude. And you can see, and thinking about your Pythagorean theorem, if I was to do it again, I get the same thing, the square root of 13. And this is where it's going to drive me crazy, and you're going to think I'm even crazier, but this line accidentally got in there, and I don't like that line being there, and I only don't really want that line for right here. And so I'm just going to give a little remove to that line with my white out here stuff. And you don't have to white yours out. Oh my gosh, that's kind of, you know, I can't fix it either because they make it where this one where you can't twist it and fix it. Okay, I won't have to be too crazy about not wanting that line there because the whiteout is not working at all. And now I've got it. Now I've got a mess. And since I can't edit, I can't fix how crazy I got here. So equivalent or equal vectors have the same direction and magnitude, but they do not necessarily have the same location for their tail and their head. So this one is going in the direction, it's over 2, down 3. And this one's going in the direction, I'm going to call it over 2, down 3. And if you're saying, hey, that sounds like slope, you're right. It kind of does. And they're the same length. They're the same length. They're going in the same direction. And so what that tells you is that this vector and that vector are equal to one another. And so that's the reason I didn't, these two statements are going together. That's the reason I didn't want that line there. And somehow in my editing, it got in there. Now they want me to draw a vector with the initial point at the origin that is equivalent to AB. Now they could have also, the vector AB, now they could have also said that they wanted it to be equivalent to the vector CD because they're equal to one another. So they want the initial point to be at the origin. So there I am at the origin, there's the initial point. And then remember how this went, it was over 2, down 3. So over 2, down 3 will be the terminal point. And I'll be able to draw this vector in here. And they told me that they wanted to call this vector V. And so I'm going to call it V and put the little vector hat on it. I don't know if I made the vector hat big enough, but I'm going to make it here. It's a line and then it's back like that to make a little vector. Sometimes when I'm tired, I accidentally push this one on my computer and get it kind of looking like that with an arrow. And I'm saying that's good too. I don't, anyway. Draw a vector with the initial point. I did that. A vector V with a tail of the origin and the head of the point. Okay, what is they want to know. I'm not on the screen and I'm showing you this. They're wanting to know what is the ordered pair of the tail. And that is a point. And so this ordered pair of the tail right here is over 2, so it's 2. And then down 3, so negative 3. And so that's just representing that point right there, 2, negative 3. But if I wanted to name this vector right here, then it would be the same as these pieces of the ordered pair of the head, as long as it's starting at the origin. And so going from the origin, then this vector V could be called, and you use these angle brackets for vector 2, negative 3. So if someone told me to plot this vector, its initial point would be at the origin, and its terminal point would be at 2, -3, and then I would draw the vector. If someone asked me to plot this point, then I would go there and I would just plot an ordered pair. I want to make sure that you understand that the difference. So if someone asked me to plot 2, -3, I would come here and I would put a point right there at 2, -3, and I would say, there I did it. If someone asked me to plot this vector right here, so a little bit slight difference on the notation, so 2, -3, then what I would do is I would plot this point right there, and I would draw a vector that went from the origin to that point and make a vector there. And, oh, I did a half dilly bopper. I didn't do my angle here. I don't know why I was talking, chewing gum, thinking about drinking a swig of my tea. All of that I was doing. Now, again, this line appeared there, and I wanted this comment to go with that. So I have to feel like I crazily have to remove it right there, and then fix where I've removed it over the top of it. I know you're shaking your head. I hope you are. This is called a position vector. So this is called a position vector. It's also called component form. So this is a position vector, and this is in component form. Okay, so next page, that was page 8 on our notes. Hot diggity dog, working hard, hardly working. I don't know. My dinner with my dad was good, so my life is pretty happy today. Formula for finding a position vector, and so we just found a position vector over there ourselves. I mean, we found the position vector by noticing slope. But if you are given a point P and a point Q, this is the this is the initial, and that is the terminal. Then you can find the position vector by subtracting the x's, x2 minus x1. I hope you remember this kind of look like slope, and then there that is the denominator of slope, and then y2 minus y1, there's the numerator of slope, and so this is called component form. Remember, a position vector's tail is at the origin, and its head is at this ordered pair, and so YEPA, this is the position vector, and this is the point. And this can be extended to 3 dimensions. So if you have the point P, X, Y, Z, X1, Y1, Z1, and Q, so this is going to be the initial, this is going to be the terminal. So if I wanted to, of the vector, if I wanted it to be in component form, if I want it to be a position vector, then I, just like I did with the other x2 minus x1, I want you to notice that Q, the second one, is first here. So that is important. If you draw them out in 3 dimensions, they're hard to draw out, but they're easy to draw out in 2 dimensions and check that it's true. And y2 minus y1. So it is important that you name the initial, your 1s, and your terminal, your 2s, and z2 minus z1. And this is a position vector. Of course, we're going to practice it a little bit here. And I know we just did this example, but I just wanted you to see that we're going to get the same answer when we use that formula. So if we, remember what it was, the vector was 2, -3, right? Okay, so what we're going to do, we're going to call this the 1s, x1, y1. We're going to call this the 2s, x2, y2. So we know, they said to call it v. So this vector here, I'm going to call it v, is equal to, and then this would be, I'm just going to write the formula, x2 minus x1, just so that no one's confused what I'm using, and y2 minus y1. And I'm going to do my little math here. So this is -1 minus -3, so plus 3. And then it is 2 take away 5. And when the dust clears, I get here 2 and then -3, just like we had before. So we were just verifying that, hey, that it's exactly the same, exactly the same. I want you to notice that if you were to do the vector, I have to take off some of my was really cold outside, and so I was all bundled up, and then I got inside, started drinking tea, hot tea, and decaffeinated, of course, and I want to stay up all night. And so if I go from B to A, then when you name these, I wish I would have given more room. I'm making a note to myself that I write bigger than I think. So here, and B, I hope that you already know what's going to happen before I even do this. I hope that you're saying, yeah, I saw that coming. And so now, since I'm going from B to A, I have to name B the ones. So x1, y1, and x2, y2. And so if I find, they said to call this vector u. So if I find u, it's still the direct same for the component x2, so I'm not going to write that. But x2 is -3. And then it's subtract x1. x1 is -1, so +1, comma. And then y2 is 5. Oh man, I didn't take roll today. How could I have forgotten that? -2. Shouldn't be thinking that kind of thing right now. And so you notice what we're going to get, and I hope that you already knew what we were going to get. We're going to get -2, 3. So yeah, if you do it backwards, then you're going to have exactly the negative of your vector. They're going in opposite directions. They're asking me to draw both of them, and if you already know what they're going to look like, wonderful. But I'm drawing them just so that to get it cemented in your head. And so V is over 2 down 3, 1, 2, 3. Of course, you already knew that. We had already drawn that one. Remember, from the origin, if it's in position vector, so that one's V. And I want to draw U, and U is over 2 up 3. And again, the same idea. And so, yeah, they're right there. They're going in opposite directions. So that's U going up there. A little better on the U, and then I'm happy. Okay, so the magnitude or the length of the vector, this is not new. It comes from either the distance formula or the Pythagorean theorem. And so if you have a vector that has a terminal side initial point P and a terminal Q, then the magnitude is given by this. And you're probably just saying, yeah, we just did that. It's basically the Pythagorean theorem, and that's definitely true. And if it's in component form, then all you have to do is square each component and do the square root. And that makes sense, right? Because the points that this would be going from would be the point 0, 0, the origin, and then to this point right here. And so if you subtract them and square it, obviously you're going to get these things. So yeah, that's really, and so if you're, if you're kind of making sure, it's because this is going from this point, right? 0, 0, to the point V1, V2. And so, yeah, you take away the x's from each other and square it, take away the y's from each other and square it, add them together and do the square root, Pythagorean theorem, right? And so it's kind of nice. And it extends exactly, really lovely, really nice to 3 dimensions. And so this would be the magnitude, boink. And if it's in component form, it's even easier. Square, add, square, add, square root, right? So lovely. We're going to practice. Of course, that was page 9. We always practice. Practice makes perfect. Okay. I know we just did this to see that the formula works. So we had just done the one, but I want to make sure that we're making sure that the formula works. So we had that V was equal to 2, -3. And so if we want to find the magnitude, this is what V was equal to. I'm going to write that up here. And then I'll write the magnitude right there. yeah, this is a little bit tight on my writing, and on the board it's okay, and I don't notice it. And so this is probably good for me to make a note to myself. I don't want magnitude around that. Because I want him to write the vector in component form. So that was 2, -3. And so if you want the magnitude, then what you do is you take the square root and you square each piece. So this is 2 squared plus, and then you square each piece, -3 squared. And so we get 4 plus 9 is 13. So this is the square root of 13. And there we have it. Oh, we're going to notice something. I don't know what we're going to notice. Let's go see what they have over here. So that's our magnitude. Now, we already had found that. We use the Pythagorean theorem. I just wanted to show you that, hey, this formula works. So if we wanted to do u, remember what u was? The vector u was -2, 3. We just got that from the previous page. So if we wanted to take the magnitude, since it's in component form, we would square it. -2 squared plus, and then 3 squared, which is 4, and 9 is 13, the square root of 13. I know that you saw that coming. I hope you saw that coming. And yeah, that it doesn't matter what the direction is, the magnitude is the same. So it's the length. It doesn't matter what direction it's going in. And so, so I guess I'm going to note something along those lines, right? I guess maybe something like this, A, B. I think this is even one in the homework that they ask you to prove that these are equal to one another. I didn't prove that they were equal to one another right now. I proved it was equal for this particular numbers, but it would be very easy to show that it was equal for all. And so a vector can be multiplied by a scalar, and this is what that would look like geometrically. So if this was my vector v, then if I wanted to draw a 2v, then I just have to draw it, what do you think? Yeah, I just have to draw it twice as long. I don't know that I should get so crazy. What kind of notes do I got on here? And so, but you know, maybe I will get so crazy. And so it should have the same direction, and it should be twice as long. And so here I have gotten crazy and I've drawn it twice as long, and I kind of measured, so I can pretty much say that it is. -v means it's just going in the opposite direction, but it's exactly the same length. So I'm going to get that same slope going here to the best of my ability. This then would be the initial side, and this would be the terminal side. And there we have -v. 3/4 v means it would be 3/4 of its size. And so I'm just going to estimate that again. So just the idea. So here's half of its side. There would be 3/4, I'm saying. And so I'm just kind of, you know, measuring just a tiny bit, not a lot. And let's see, we're still going in this one is wanting to be 3/4 of that one. And so all of these should all be parallel to one another to the best of my ability. I drew them parallel. And so that's kind of the idea there. Okay. Now a vector in component form can be multiplied by a scalar algebraically. And so if you multiply this vector right here by the scalar k, they're using k for a scalar, and that's just any number, then k times the vector v is equal to multiplying k by the components. And that can be extended to 3 dimensions just the same. And so each multiplied by k. So we're going to give a try to that, and we're going to draw it, and you're going to see it's twice as long. It's going to be beautiful. And what is the deal with my stories? I got to get Kevin down here and help me with my setup. Again, my yoga block keeps like merging out and making it where I, you know, it's the working conditions around here. So if they weren't wanting me to find 2v, then 2v is equal to 2 times the vector 1, 3, like that, which is equal to multiplying them both by 2, so that's 2, 6. And so it's asking me to draw both of them. This one right here was 2v, and it's asking me to draw both of them on here so that you can see that they're in the same direction and double the size. So I'm going to draw v first. So it's over 1 up 3. So there it is. And it started there at the origin. You can draw it anywhere though if you wanted. You can start it here if you wanted. It's over 1 up 3. And it's equivalent vector, right? And so there it is of V, and I drew it over there. Now I'm going to draw 2V, and its terminal is 2, 6. So over 2 up 6. And you're going to notice that when I draw it in here, that it goes right on top of, it's parallel, and it's twice as long. That one right here is from here, if I drew it, over 2 up 6, it's twice as long, right? It's twice as long as this one, and it's in the same direction. So yeah, so we did a lovely job on that. Now we're on page 11. So it's telling me here on page 11, 2 vectors can be added together geometrically. And so we're going to do that. And what you do is you put them head to tail. Is what you do. So if I wanted to draw here, they're asking me to do the vector u plus v. And so I'm going to draw u in here to the best of my ability. So, you know, I'm trying to draw it parallel to that, and I'm trying to draw it the same length. And I'm trying not to get too picky about, you know, just doing my best as I tell you. That's what I'm doing. So this is u. And so here's the head on U, and so it's head to tail, so you're going to get the tail. Here's the tail of V, its tail, and you're going to put it right here, and I'm trying to draw it so that it also looks parallel to V and the same length as V. And so this right here is U plus V, but there's one more piece to it, and that is that you draw this all together, this whole thing, and I'm trying to draw it straight from that tail to that head. And this is the vector u plus v right there. And then the parallelogram rule, they think it, I mean, you know, everyone acts like it's something, but to me it's like, oh, well, you know, yeah, I think I could have guessed that. So I'm going to draw on here the best of my ability u to the best of my ability v. There's u, and here's v. And then if I do if I want to look at v plus u, so I'm going to come here. I'm going to start here at the same spot, and if I do V first, trying to draw it the same as this, V first, so there's V, and so they're trying to start here at the same spot that I did here, and then if I do U, it should meet at the same spot right there. And this is the parallelogram rule. And so if I do U and then V, or V and then U, and I start at the same spot, they should end at the same spot. That's all, and it makes a parallelogram there. And of course, going in the middle is U plus V or V plus U. They're equivalent to one another. So we did a lovely job on that. 2 vectors in component form, so I'm reading right here, can be added together algebraically, and it's easy. Thank goodness it's easy. You won't have to do anything fancy or anything. Not everything is easy. So some multiplying you're going to notice is, what? Are you kidding? To do all that to multiply? And there's 2 forms of multiply. Oh, okay. But adding is really easy. You just add the components. And so the first component and the second component, add them together. If you have in 3 dimensions, then all 3 components. So that's all you have to do. So here they're asking me to do u, the vector u plus the vector v. So if I do add those, this is adding 1, 2, that's u, plus v, which is 5, 3. And all you have to do is add the components. 1 and 5 are 6. and 2 and 3 are 5. And of course, I asked you to draw them all because, and I really do think that, you know, you should probably pause the video and draw them all just to practice it. So 1, 2, try these on your own, definitely. And then 5, 3. Oh yeah, I remember this story. I want to draw a 5, 3 because I'm wanting to do U plus V and to show that it's 6, 5. So I'm going to do it head to tail. And so 5, 3 is here over 5 from here. 1, 2, 3, 4, 5, up 3, 1, 2, 3. And so this goes here. And then if you, and so here we have that. Oh, man, Donna. I think you can write on these and correct them a little bit. And then if I go from here to here, I ought to be at 6, 5. So when I added them right here, this ought to be having a terminal of 6, 5. Do you guys notice that it is? It's over 6 up 5 from there. And so, yeah. And so this is right here is U, this is V, and this is U plus V. So we did a good job. We drew them all on there. And then 2 vectors can be subtracted geometrically. So we're going to subtract them geometrically. So here's the idea if you're doing subtraction is that, remember that subtract is add the opposite. And so this would be U plus, and then the opposite in the other direction of V is what that would be. And then if I want to draw this to see what it would look like, again, I'm complaining about my working conditions here, then I'm going to draw U. So I'm going to draw U the same, trying to draw it parallel. I don't know if I got it too parallel. I'm pretty off on my paralleling today. I wonder why I'm so off on my paralleling today. Okay, that's better though. And then I'm going to draw V. And so here is, so this is head to tail here. And I'm going to draw V. Oh, that V is that same V that we had. But I want to draw the other way. So it's going to go the other way. And so when I draw it going the other way, this is how it looks, so that you can just see. This is how it looks, right? And so remember, you wanting to come over here and put that head to tail, right? So right here is where this goes. So there's the head of U. And then this right here that I'm drawing right here is negative V, is what it is. And so this from here, from this initial point to that terminal point right there is U. Maybe making an arrow like that is not the best way, but this is U minus V. Is what that is, that little length right there. Okay, so we did a lovely job on that. Subtraction is easy, just like addition was. That if you want to do U minus V, you just subtract the components. If you want to do 3 dimensions, you subtract the components here. So this is U1 minus V1, U2 minus V2. So this would be U3 minus V3 is what it would be. So you just subtract the components. So I ask you to do that, and I ask you to draw a few of these just to kind of, just to make sure of how we're, just to make sure of how we're going and how we're doing. And so we have 1, 2, that was U, minus V, which is 5, 3. And so when I subtract them, is 1 take away 5, negative 4. 2 take away 3, which is negative 1. And so that is the subtraction. And it's asking you now to draw them all on here so that you can see. So 1, 2, So here's here. And it's kind of wanting to show that that same thing kind of going along. What I did when I drew it is the first time I drew it is I didn't put them head to tail and tail to head and all of that. I just went over here because it's kind of interesting what happens. You can do that on the other and kind of see too. And so if I come over here and I draw 5, 3, 1, 2, 3, 4, 5, 3, 1, 2, 3, and you get this going here. Should have made a dot. And I'm like, what the heck? That's not giving me what I wanted. Well, remember that that I can move this around anywhere that I want. And remember that I wanted to subtract. So I can take this vector right here and go the other way. That's what I needed to do. So this was over 5 up 3. So it's over 5 this way. 1, 2, 3, 4, 5, because I want to subtract. And then down 1, 2, 3. And so this vector right here is really, and then now when I do that, do you guys notice where I ended? Well, I ended at -4, 1. And so definitely good there. So this one right here was my vector v, is what it was, right? That's my vector v. But really I wanted to draw my negative vector v because I want to add the negative of that, because I'm adding the negative of that. And you notice that it did definitely give me the same answer, which is -4, -1. So anyway, kind of, it's nice they all work. These are the properties of vectors, and they're not real hard to prove. You can think about them. You can prove them in R2 or in R3, either way. And I bet you know and remember some of the names of these. Like this one is the commutative property, the associative property. And so I bet that there's some that you see and that you remember. How are 2 and 3 different from one another? Did I have a typo that I didn't notice from last semester? Those are the same. I didn't notice that. I wonder which one I forgot. Go look in your book and see which one I forgot and put it in there, because I'm sure that it's a typing problem is what it is. So if I want to prove this, then what you could do to prove this is you let u equal, and then I'm going to let it be the vector u1, u2, u3. So I'm going to prove it in 3 dimensions. You could prove things in 2 dimensions. And so if you're going to add these together, then all you have to do is just show that this is u1, u2, u3 plus, and then the negative of u, well, that is negative u1, negative u2, right? You distribute the negative, negative u3. And so if you add these together component by component, right, you get u1 minus u1 is 0. u2 minus u2, if you add them together component by component, you get 0. And you get 0 here. And that vector with 0 in all 3 spots is called the 0 vector. And there's notation for the 0 vector, and the notation for the 0 vector is 0 with the vector notation in it. Anyway, so there you kind of have that. And I said, hey, for a challenge, go and show all of these are true in R2. It extends really easily to R3, but you could give a whirl to it. They're not too hard at all. And so if you're trying to do it in R2, then the 0 vector in R2, you can't see what I'm writing. R2, the 0 vector looks like this, 0, 0. And in R3, the 0 vector looks like this. Okay, so we did a lovely job at looking at that. So you can prove all these properties. Now I'm curious, boy, that was, I wonder, I'll have to go look and see which one, which one did I not put? Or did I just, I don't know. I don't know. Okay. So another note is that there's the vector I and j are vectors because they're I and j are called unit vectors. And when you have them, you can use a little hat on them. And so I is the unit vector, and I'm gonna print it. I looks like this in the little hat. When I do it on my computer, it like loses the little dot. It also loses it for j, and it is a unit vector. Now what it means to be a unit vector, did I miss a page? Because I thought we did do a unit vector before this. But I'm now telling you what a unit vector is when we haven't done one. Where was the unit vector at? The unit vector is length 1, so it's not a big deal. And you can definitely verify that this is length 1. Here it is drawn here, and j is drawn there, and they're both length 1. I don't know what the deal is. I think that we're going to do a unit vector here coming up, and so, but your book uses bold I and bold j, just like they do on the vectors. They use bold v, and so when something is a unit vector, I try to use the little hat to show that it's a unit vector, but sometimes I forget and just use vector notation. When you use the little hat, you're just really advertising to everyone it's length 1 is what it is. I is always the vector 1, 0 over 1 up 0, and j is always the vector 0, 1. And so anyway, these are called the standard vectors is what they are. And they're both length 1, and they point in the positive x direction and the positive y direction. And so they prove this in your book, and I thought at the time I left room to prove it as if it was going to be I don't know, mind-blowing, but it's not really all that exciting. But I'm going to show it to you anyway, that there's another form that you can write this in. And so this can be written, you'll agree, as, and particular, you know, I'm purposefully writing this. So if you're saying, well, how did you know how to write this? And it's because I know where I'm going. But it's true. I know where I'm going with this. Even if you're saying to yourself right now, I don't know where you're going with this. But there's another way that vectors can be written. And so I want to write it like this just for a second. And the reason that I'm writing it like this, then I can separate this. And so I'm going to call this one of my vectors right here. So this vector, and just verify that it's true. This vector here, and 0, not thinking, plus, and then 0 and v2. I was having trouble thinking because I was also thinking about my tea and whether I would get ice cream for making this video. Hopefully I remember to push play. Record on the thing. Now I want to factor here out v1 and just verify that if you added these together, you would get this. If you combine like terms, that you would get this. Yeah, definitely would. Now I'm going to factor out of v1, and when I do factor out of v1, and here I'm going to factor out of v2, just verify that if you multiplied it back together, that you would get v1 times 1, v1, v1 times 0, 0. v2 times 0, yes, yes. And so do you now see where I was going with this? Here's 1, 0, right? What is that called? It's called I with a little hat, right? And what about here? That's called J with a little hat. So here we could write this v1I, with a little hat plus V2j with a little hat. And so that's another way of writing the vector. So you have component form right here. And this is, some people call this IJ notation. I'm good with that. Kurt Klopstein calls it a linear combination of the standard unit vectors. That's a mouthful when IJ notation. And I just put the thus here. This is what, hey, what we found. We can easily extend this to 3 dimensions. So here's IJ and K. And so K is pointing in the Z direction right there. And if I wanted to write this, just extending it, not proving it or anything, start writing it out. What would it be if it just kind of extended? And so I think that you probably already have gotten it going. Pause the video if you're worried I'm going to write it when you were going to write it without me. And so, V2 and V3. And so there we have it. And that's IJK notation. And it might be too early for vector jokes, but you can check it out and see if you think it's funny. If it's, but maybe it's a little too early for vector jokes. I don't know. Okay. So here's how to find a unit vector. So those vectors were definitely unit vectors, and we didn't have to worry about finding them. But if you wanted to turn anything into a unit vector, you will strip it of its magnitude if you turn it into a unit vector, because now it'll have magnitude 1, but it'll still have the same direction. And so there's times that we want to do that. So a unit vector, and they use the little hat to show that it's length 1, is in the same direction as the original vector. And all you have to do, if you have a vector A and you want to make it into a unit vector, all you have to do is take the vector A and divide it by its magnitude. And then you'll have it going in the same direction, and it will only be length 1. And of course, I can't help it. We have to do them and draw them. And we're doing this and drawing them so that we can see that, yes, it made it length 1. And so they're asking me to draw A and U when we're all done. And maybe some equivalent vectors as well. So I'm going to draw A. So from the origin over 3 up 4, 1, 2, 3, 4. So it ends here. And this is A. And then here's an equivalent vector. So I'm going to start it here, and it's over 3 up 4. 1, 2, 3, 4, because it said to draw maybe some equivalent ones. Now I haven't found you yet, but I'm going to find you. And when I find you, I'm going to say hello. Haha, that's just a little joke. And so, not very funny one though. I can do better. Maybe I can't. I don't know. So here's the formula for finding the unit vector. It is your vector divided by your vector's magnitude. And so I didn't find my vector's magnitude, but maybe I'll go over here and do that. So remember how to find the magnitude. If you're saying, I don't quite remember how to find the magnitude, pause the video and see if you can remember, and then put it on, and I'll be talking about it some more. So remember, what you do is you square the components, add them together, and take the square root. So in this case, or you can use the Pythagorean theorem if you want to take the time to draw it. Definitely. And so we're getting 9 plus 16, which is the square root of 25, which is 5. And so you probably could have saw that this was a 3, 4, 5 right triangle, right? And so the magnitude is 5 there. And so here we have 3, 4, that's what A is, and then divided by the magnitude. I just found that up here, which is 5. So this is the vector U, looks like this: 3/5, comma, 4/5. You can verify, if you like, that that has length 1. The reason I said to draw a few equivalent ones, because guess what's going to happen when I plot this? I'm going to go over 3/5, which is about here, and I'm going to go up 4/5, which is about here, and I'm going to draw it, and then see how you can't see it, because if I draw them starting at the same point, 0, they are in the same direction. So that's the reason I said to draw a few others. So I'm going to draw one right here. There it is, and it is length 1. If you're thinking, no, it's not long enough to be length 1, well, one of these boxes is 1, and if you go all the way straight across to the other side, all the way to the other side, it's the square root of 2, right? 1 using the Pythagorean theorem, 1 on the sides, and then you add them, and that gets 2, and then the square root of 2. And so that's the square root of 2 in length is the diagonal here, and that's around 1.4. And so that's, closer to 1.5 than to 1. Well, I don't know. Yes, it's definitely closer to 1.5 than it is to 1. But anyway, so that's kind of the idea. Okay, then a note that almost can get lost here because of my boxes. I'm so boxy, and then this one could almost get lost. But 2 vectors are parallel if they are scalar multiples of each other, and so consider these vectors. And so we have u there, and so these are all new vectors, and here's v, and here's w, and it says which of these 2 vectors are parallel, or are they all 3 parallel with one another, or none of them parallel with one another. And I noticed that one scalar multiple, meaning multiply by a scalar, right? So if I have 1 and I go to 5, that would mean I'd have to multiply by 5. And if I go from 2 and I multiply by 5, then I would not be at 3. So they're not scalar multiples of one another. But these 2, if I wanted to go from u to w, looks like I would multiply by 3, right? So times 3 would give 3, times 3 would give 6. And so u and v, w, not v, are parallel. And the reason they're parallel is because w is equal to 3 times u, right? If I multiply this by 3, then I get that one. Exactly. And so that's the reason. So they're scalar multiples of one another. Now, the other way I could have written it, I could have said that u is equal to 1/3 of w. And that would have been also correct. And they would have also been scalar multiples of one another. So my choice on that. They're asking me to draw u, v, and w and some equivalent vectors because they're just wanting me to see that, oh yeah, they look parallel. And so we've drawn these a dozen times. So there's 1, 2, there's that vector, and here's an equivalent vector. 1, 2, over 1 up 2. There's an equivalent vector. That's u that I've just drawn on there. U. Here's u. And then when I draw v, over 5, 1, 2, 3, 4, 5, up 3, 1, 2, 3. So it's going to go from here. I don't think I'm going to draw any more of v. And then w, and you can see that it's not parallel with u. These are not parallel, those are not parallel. And then w is over 3, 1, 2, 3, up 6, 1, 2, 3, 4, 5, 6, right here. And yeah, when you draw them both with the terminal point, the tail being the origin, then they are going to go right on top of one another. So I'll draw another one right here with a different place. So over 3, 1, 2, 3. So that's why I said some equivalent ones. 1, 2, 3, 4, 5, 6. And you can see that this is W, right? And you can see that they are, they're parallel with one another. And some more jokes about vectors that you might not be ready for, but come back on them because they're funny. So you can come back on those when you're a little more ready, maybe after you've done some homework on them, and then you're like, oh, that's hysterical, that's what you would say. That's absolutely hysterical. So now I'm on page 15. So page 15. Of course, I'm getting that fixed. That's going to be fixed as soon as possible, as soon as humanly possible. I'm going to have that yoga block fixed, so it's not so in the way. It wasn't in the way last semester, so I don't know what's made it now in the way. Can't stop. Got to stop thinking about it. Okay, P is this and Q is this, and it's asking me to find the position vector PQ. Pause the video. I think you can do all of these and see what you think, and then come back. Okay, I'm assuming that you paused. Did you pause? And so because I'm going from P to Q, when I name this is X1, Y1, Z1. And this is X2, Y2, Z2. And so when I go from P to Q, then you do the X2 take away X1. So it's -5, take away 2, comma. The next one is 2 take away 3. So the most common mistake that a person makes in calculus, 4 take away -4, is not to show their work in any way and make an arithmetic mistake. So I have no idea what you're doing. And so you probably don't want to do that. It's probably not even a bad idea to write out the formula. And it might be, I told you, that people were more likely to take test 12 again than they were to take any other test again. And if I'm not mistaken, arithmetic was huge on it. And so writing out, I mean, so you want to get as many points as possible. So showing me that you know what you're supposed to do, but you've just made an arithmetic mistake. Whereas if you don't show me what you knew what was supposed to do, so I don't see your arithmetic there, I just assume that you've done it wrong because I have no way of knowing what you've got going. Hopefully, I'm not going to make an arithmetic mistake. I might, though. And so, but I would give myself, because I've written the formula, I've written what I'm trying to do, I'd give myself, you know, some good part of my credit here. Now it's also asking me to find the magnitude. And so I'm hoping that you went and did this on your own. So you do the square root, and if you have it in component form or you have it as a position vector, then you square the pieces. Again, if you don't show your work, I have no idea what you've done. So it's 49 plus 1 plus 64. And then when you make a boo-boo, I just have to assume that it's not right. And so because I don't know what you've done. And so that's just, when I add those together, I'm practically having my fingers out right here because I realized that I didn't put my calculator. I thought I had got my calculator out, but I hope it's the square root 114. Send me an email if it's not. Okay, now they had told me to find that position vector and call it A. So I think I'm going to write that right here. So A, just so that I kind of follow that one little part that seems like I didn't do at first. So there's A. And find this. So I just found that. So I think I'm okay there. And then, oh man, there's a typo right there. Fina instead of find. Right there. Typo. That's for me to fix for the real students next semester. So typo right there. Maybe if you're watching this video next semester, I've already fixed it. Or maybe I didn't. I don't know. We'll see. Okay, it says find a unit vector for A. Just note, A would be parallel to the unit vector, and parallel vectors are scalar multiples of each other. So it's just noting some things there, and yes, we're definitely going to see that that's true. So if they're wanting me to find a unit vector, they didn't say to call it U, but I think I will go ahead and call it U. So that unit vector would be the vector A divided by its magnitude. And good news, I have found those things, -7, -1, and 8, in the previous, right? This right here is really the magnitude of A, or also the magnitude of A, which square root of 114. I wonder if that reduces. I didn't even think that it might reduce, right? And so here you can see that these are scalar multiples of each other. What would I multiply? I should have used this, huh? Because it's a unit vector, so I should use the hat to really get to use some of my notation. It wasn't wrong what I had, but since it is a unit 1, I might as well advertise. Yeah, you would multiply a by 1 over the square root of 114 is what you would do in order to get u. Or you would multiply this by the square root of 114 in order to get that. So yeah, they're scalar multiples of one another. And so definitely, so they just were noticing, wanting me to notice that. Yeah, I noticed that. If someone asked me to find u, I think I would go ahead and write it like this. I probably even would rationalize the denominator, but I'm not up for it today. And the book is about 50-50 on that. Okay, write A in IJK notation. And remember what Kurt Klopstein called this? He called it a linear combination. So instead of the IJK notation, he called it a linear combination. Telling you this about him because guess what? You might have him for 6D. And so I want to make sure that you have all of the words, not just some of the words of the standard unit vectors. They might also ask that in that note, in this way, in the textbook. They might also ask that on a lab. I guess the labs were written by me in union with other people. And so I get my lab questions from everybody I know. Professor Leonard on YouTube, my good friend Becky Head, Arnie Andrazian, Kurt Klopstein, and Thomas Mee have all helped me have my lab questions that I have. And so anyway, so we're going to write A in the standard. So here is, remember this one was A. I got it up here. Here is A. So it's negative 7I hat, and then minus 1J, and then plus 8K. And so I did a lovely job on that. Just beautiful, just beautiful. And then it says here next, if we have this vector B, and there it is, and they want me to find 4A minus 5B. So this, they're wanting me to find here 4A, A was negative 7, negative 1, 8, minus 5B, 2, 5, negative 3. So this would be negative 28, negative 4, and 32. I hope you're doing this yourself. And then if I put the negative 5 in, then it would be an add, right? And if I just put in 5, it'd still be subtract. So my choice on that, you do you, or I guess you can probably do all the math in one fell swoop. When you do too many steps at one time and you make boo-boos on it and you haven't showed me what you've done, then I don't know what you've done and then you can't get part credit. So I do recommend writing out what you kind of got going. So now I'm going to have negative 38 and I'm going to have negative 29. And I'm going to have, my gosh, I wish I had a calculator, 47, I think. And so there you have it. So we did a lovely job on that. And just when we didn't think there could be any more, we're on page 15 still. How many pages do we have to go to? Oh, just one more. I might make it. I might make it without passing out and not needing and not getting any ice cream. I feel like I should be getting some ice cream or something. Okay, it says, what does it say? What is the angle between the vector, which looks like this, and the x-axis? And they want it in degrees and they want it in radians. Okay, so I'm going to draw it because I think that might help me. I wonder if I should draw it right there in that spot right here. So it's over the square root of 3 in the I direction. Move up, Miss Donna. So here is 1, and the square root of 3 is around 1.7. So here is 2. So I'm going to put that right there, the square root of 3. So I'm over the square root of 3 and then up 1, this 1j, right? So up 1, and this distance right here is 1. So up 1. So this is here, right there. Now, if you're saying, now the way you plotted that, I don't get it, well, you could write it back in vector form. If you wrote this in vector form, it would be the square root of 3, and then j, 1j, would be 1, right? And so this would tell me over the square root of 3, up 1. So now they want this angle right here, between the x-axis, this is the x-axis right here. So the angle, the x-axis, this I'm going to call it theta. What the heck? You call it, you do you. Call it whatever you want. And I thought I would whip out some of my trigonometry. And my trigonometry I taught myself. And so I have to write everything out. And so on my trig, you might know your trig a little better than me because you might have had somebody teach you like a teacher. Susie could tell Oscar had a heap of apples. You do it any way you want. And here is the right angle in here. And I know this distance is the square root of 3. And I know this distance is 1. So I know those sides, 1 and the square root of 3. And so what I need to know is the hypotenuse. I don't know the hypotenuse, so I don't want to use one of these friends that has the hypotenuse in it because I don't know the hypotenuse. Now I could take the effort and go find the hypotenuse if I wanted, and then I could use sine and cosine, sine or cosine, but I'll just use tangent because it's available. And so the opposite is 1 over the square root of 3. So what I know is the tangent of theta equals 1. That's the opposite divided by the adjacent, which is the square root of 3. So 1 over the square root of 3. And then I need to know what tangent is, and I know that it's an acute angle. And I have to tell you, you can use your calculator. If you use your calculator, you're going to do the arc of this 1 over the square root of 3, and that's going to equal theta. But these are ones that when I taught myself, I just sort of almost memorized. And then sometimes I have to go and check them. And of course, I'm here without a calculator. And so I'm hoping I'm right. I'm almost wanting to dig through my bag and get a calculator so that I can verify that I'm right. I can't believe that I got here without a calculator when I knew it was because my brother called me. Blame my brother. I think it's 30 degrees. Am I right? And I know that 30 degrees goes with pi over 6, right? Oh man, I wish I had a calculator. I don't though. I do not. Okay, I hope I'm right. Maybe a little prayer on am I right? Okay. Oh no, I'm going to have a calculator here. What is the angle between the vector this and the x-axis? So we're going to draw it 2 here. And over 2, don't make that all that distance 2. Over 2, up 5. So that this side here is 5, and this side here is 2, and this is my angle theta. So they asked for the exact, so we know that tangent of theta equals 5 over 2. So that theta equals the arctangent of 5 over 2. And that's the degrees. This is exact in degrees. So theta equals tangent, arctangent of 5 over 2. So that's the exact value in degrees. Now they want me to round it. And of course, I'm not going to be able to do the math on rounding that without finding a freaking calculator. I hope that you pause the video and look it up, but I'm on one shot on it. Arctangent Sorry about the dead airspace. I really needed a calculator. I've been suffering without one all of this time. Got to make sure that my calculator is in degrees. So I have my calculator. I have it in degrees. And I need to do the arctangent of 5/2. And I get 68. They said to round to the 10th. So this is the 10th spots right there. So 68.2. I'm showing you how to round there, and that's in degrees, and rounding correctly there. And people tell me in my Calculus 3 class that they don't know how to round, and that they shouldn't have to know how to round. And I think if you're in Calculus 3 and you don't know how to round, come, I'll help you. I'll teach you. I know you can do it. And then we'll be all done with that. We won't have to talk about it anymore. Okay. Now, I know they make you round to all kinds of places in physics and chemistry. I know they do. I took those classes. Okay, 1, 2 last problems, thank goodness. And then we'll go to our houses and we'll lay on our beds. Oh, wait, I'm already at my house. I can just lay on my bed over there. Oh, no, but I have papers to grade. Anyone want to come over and help me grade algebra papers? There's 100 of them. Okay, a child pulls a wagon with a force of 20 pounds at an angle of 30 degrees in the 30 degrees to the horizontal. Find the horizontal and the vertical components of force, and find the force vector F. So we're going to draw a little thing kind of going here. So we have, I'm going to draw in here. So here she is pulling, and here is her angle right there, theta, which I think they said was 30 degrees. And then right here, she's pulling on this handle up here, and it's really straight there. And that's her force. And in fact, really, I'm going to draw this out here just a little bit better here. The magnitude of this force that's kind of going here, they said was 20 pounds. And this angle right here, they said was 30 degrees, right? And then they wanted me, I'm going to just extend this and make it just a little bit bigger. They wanted me to find the vertical and the horizontal component of force. And so the, her little pulling on her wagon, this right here, the up and down, is the vertical component, P-O-N-E-N-T. And I can find that. I can call it whatever I want. Would it be okay with you if I called it A? So I'll call it A. And I know, and I got the hypotenuse. Remember, did you guys remember? Susie could tell Oscar had a heap of apples. Every time I say Susie, because that's the name of my cat, she pricks up her ears over here. She's like, what? Talking to me? And so maybe I shouldn't call it A. I'll call it X. Maybe I should call it Y. That would even be more clever than calling it X. Do you see why it would be more clever to call it Y? Okay, kind of tired. So let's see here. We know the hypotenuse and we know the opposite. So we know sine here. So this is the sine of 30 degrees equals y over 20. And the sine of 30 degrees is the sine of 30 degrees half? I think it is. So this is half equals y over 20. And so all of a sudden I know that y is equal to half of 20, which is 10. And that was the vertical component of force. Now the other thing that I wanted to find was the horizontal component of force, which is right here. Horizontal, this magnitude right there. Horizontal, that length component. And let's see, that one was sine, so this one's going to be cosine. So cosine, I'm going to call this side here x, of 30 degrees equals x over 20. And the cosine of 30 degrees is it the square root of 3 over 2? Oh, you have your calculator now. You don't have to sit there and wonder if you're right and think, yeah, it is square root of 3 over 2. Equals x, and then over 20, and then we're going to multiply by 20. And when I do, I'm going to be out of room here. I write so big, and so here I'm going to get 20 times the square root of 3 over 2 equals x. So I kind of merged over there, and that is 10 square roots of 3 equals x. And that was the horizontal component of force, and this was the vertical component of force. And they asked me to find both of them, and then they asked me to find the vector, the force vector. And what the force vector is it is the horizontal and the vertical components of force. So I found the vertical component. I didn't say what it was 10 pounds. So I'm going to write that right here. So 10 pounds, right, because we had units. And this was here 10 square root of 3 pounds for the horizontal. And so here our horizontal, our over, is 10 square roots of 3, and our vertical was 10. And so there we did a lovely job on that. It was beautiful. Then we have another one to do. Woohoo, 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 and then we're done, I think. And then there's one for you to do, but good news is that try it yourself if you want. It's a hard one. The algebra gets nightmarish, literally, and whatnot. And I think 2 equations, 2 unknowns. I think everything's involved. I think it'll take this whole page, and it's in your book. And so you can check it out there. A woman in a rowboat paddles due west at 4 miles per hour in a current that flows northwest at 2 miles per hour. Find the speed and the direction of her rowboat. And so we're going to give a try to that. And so we kind of have a couple of things going on here with this woman going. We have her in her little rowboat. Here's her rowboat. And if this is north here, and I'm going to draw this here, this would be west over here. And it said that she was going due west at 4 miles an hour. So I'm going to draw this over here going due west, and the magnitude is 4 miles an hour. So I'm going to draw at a length of 4. And so right there, we know this is right here. I'm going to call it R for rowboat, and the magnitude of that rowboat right there is 4, is what it is. And so if I wanted to know what the vector R looked like, it's going this way, so that's -4, 0. So now I've got some stuff on the rowboat. Now I would like to make some stuff about the current as well, and then we'll look at what our plan is to be. Remember what they're asking us is they're asking us to find the speed and the direction of the rowboat, and that's the speed is a vector. And so here's what's happening with the rowboat, just so you can maybe see that where I'm going with this is the speed, which is a vector for the rowboat, is equal to how the woman is paddling in the direction she's paddling, so that's R, plus, and then I'm going to make another one, and I'm going to call it the current is what I'm going to call it. And what the current is doing, I haven't drawn the current picture yet, but I'm going to draw it. But I already know what R is, -40. And I want to find what speed is. That's what I'm wanting to find. And the vector for speed. And then I can find the magnitude, and then I'll know the speed. And then I'll have my vector. And then they actually, this problem was in your book, and they actually gave the answer as with north and west in it. So we'll give a try to see if we can do that. It gets pretty nasty, I have to admit. So anyway, so that's kind of where I'm going with this. So this is my current right there. So that's going to be my vector for speed. It's going to be my rowboat plus my current. Now I'm going to draw my current. I'm going to draw that right here and try to get all the stuff about it. So this is north and this is west, and they said that the current flowed northwest. So they didn't say like more north than west. So when they say northwest, that's just right in between. So that's right here in between, and the length of this vector, I'm going to draw it, is 2. Because it's 2 miles an hour. So the length of that vector right there is 2. And so the current right here, there's eraser dust, is equal to 2. And so what I want to know on this, so that I can get the current vector, is I want to find, because I want to know where this is right here, that vector right there, where that goes. Oh, did I say that this was 45 degrees right here? Or did I just tell you right in the middle? Right in the middle. So right in the middle there. And I know that the length of that is 2. And I want to find the horizontal and the vertical component of that. And so if I go to find the horizontal component, the horizontal component, just like on the one that we had up here, is the cosine of your angle, and then over, and then your hypotenuse, right? In this case, my hypotenuse right here is, this is what this is, C equals 2 is what that is. And it's too small. I have it drawn too small. And you're like, well, you're the one that drew it too small, so you should draw it bigger. Well, it was because this was 4, so I was trying to draw this to be looking half the size of it. But I got this triangle in here that I'm blowing up here, which is 2 here and 45 degrees here. And I'm wanting to find this right here, which I'm going to call X, and that right there, which I'm going to call Y, is what I'm wanting to find. And I'm going to just use my trig to find it. X is the horizontal, and so that is the cosine of 45 degrees, right? So I'm looking at this and I'm saying to myself, oh my gosh, is my pencil running out of ink? Lead, whatever. Yes, it is. Is it done? Is that possible? And so this is the cosine of 45 degrees equals, and I said I was going to call it X over 2. So this is 2 times the cosine of 45 degrees equals X. And so that is equal to, I'm going to use my calculator now, and be careful. I have not been careful, and that X, because of the direction it's going, should be negative, just like the 4 was. And so, well, I haven't not been careful yet. I'm just finding it as if it was on a triangle right now, and then I'm going to go back with where is X. It's this direction, so it is negative. So this is 2 times the cosine of 45 degrees, and that is the square root of 2 times this, what is wrong with my calculator? I put that in. That's not the answer, right? The square root of the cosine of 45 degrees is square root of 2. And if I multiply by 2, what is going on with this crazy calculator? Am I going crazy? degrees. What is the coat? Horizontal. Adjacent. Did I make, I've done this problem before, and I'm thinking, that I have a mistake here on my paper, because here, when I do this, but I think I made a mistake when I did it before, or am I making a mistake now and Kevin has to fix this? I think I'm getting square root of 2 here for x, but this is negative, and the vertical, which is here for y, which is positive, sine of 45 degrees. That is the hypotenuse, equals, sine is the opposite, so 45 degrees is here, opposite is y, over the hypotenuse 2, and 2 times the sine of 45 degrees is equal to y, which is equal to the square root of 2 equals y. So this one, our C, for our current, should be equal to, for x, it should be negative square root of 2, and for y, it should be positive square root of 2, should be our current. So then, having these two things and having something different the last time I did it, oh gosh, into the crack there. I'm not going to be able to write that. Did the best I could. So when I add these together for my speed, I'm going to get negative 4 minus the square root of 2 and the square root of 2. And so that is my speed vector, right? And so now I want to do the magnitude so that I know kind of what the speed is. So the magnitude here of s, square root and square the components and add them together. And this is not something that's a nice answer, but I'm going to put it in my calculator to get a lovely answer on it. Let's see, -4 minus the square root of 2 squared plus, and then when I do that, I'm just going to, that's just 2, right? So I'm going to put that in there, 2. So I'm getting the magnitude here is 5 point, for the speed is 5.6 is what I'm getting when I put this in. 5.6 if I round to the 10th. If I did the exact value, I think I could probably make my calculator do the exact value, but I'm not worried about that. So 5.6 miles per hour, rounded to the 10th. And this is the speed that she's going. And now if I want to find, the direction that she's kind of going in, you can say that that's north, west of north, or you can do north of west. So that's kind of my choice of what I want to do, because what's happening is she's trying to go across with her boat and the wind is pushing her, and so a little bit off course a little bit. And so and it doesn't matter if which one that you find, and so that doesn't matter at all. So what I'm going to draw it in here, and then we'll write it, and then you can change it if you like. But if you go in here, and I'm going to call this S, the vector S right there, and I'm going to find that right there, which is that theta right there. Now we know what S is. It's 5.6. And so if we're trying to find that theta, I'm going to draw it in here so I get a right triangle, right? And so what things do I know is that S had that distance, -4 negative square root of 2, and so that's this distance right here is what that distance is right there, right? Because it's this distance, it's how far over, and then it's up the square root of 2. So I know for this S, I know right here, I know this is the square root of 2, and I know that this here is, and it's, I'm wanting to do trig on this, and so I'm going to go ahead and make that, because it's a distance, so I'm going to call it 4 plus the square root of 2 over, because I'm just kind of finding this triangle, so 4 plus the square root of 2, if you'll allow me to do that. So I'm wanting to find out what theta is, and so the things I've labeled are the opposite and the adjacent, so I can use tangent. Tangent of theta equals, and then it was opposite, which is 4 plus the square root of 2 over the adjacent, and the adjacent is the square root of 2. And so that will give me the angle theta. I'm going to use my calculator. So theta equals approximately equal to the arctangent of this value right here, 4 plus the square root of 2 over the square root of 2. And so we're going to see what we get here. So arctangent and fraction 4 plus the square root of 2. In the denominator, I'm going to have the square root of 2. And I'm getting there 75.4 if I do to the 10th. Degrees is what I'm getting there. And so this, if I was north, right, I would be straight up and down, but I've been pushed over this direction. And so how you would say this is that I am 75.4 degrees west, because I've been pushed west, of north. And so that's how you would write, how you could say that. Now, when you look in the back of the book, they use a different notation, and the notation that they use is this notation. So that if I was started off north, and then I am 75 degrees to the west is when I'm over that way, 75 degrees. And so if you wanted it to say it the other way, you certainly could. If you wanted to say it the other way, then you would be finding this angle right in here. And if you find that angle right in here, so this is S. And if you find this angle right in here, and I've of course drawn it not to scale, but if I want to find this angle right in here, if this angle was 75.4, well, that angle there would be 90, take away 75.4. That angle there would be 14.6 degrees, and that would be north of west. And I wasn't the one that made up the notation, and this would be west 14.6 degrees north. I just learned it, I guess. And so other than making myself crazy, because when I did this problem the very last time, I said that 2 times the cosine of 45 degrees was 2 square roots of 2, and it's clearly not. And so it made me, it's like I peeked over there, you know, and when I peeked over there, I have something different. So I'm like, oh, when did I make the mistake, now or then? And I'm pretty confident that it was then. And so anyway, oh my goodness. Okay. I got long there at the end. Do that problem right there. See if you can do it. I'm going to do it too. And I'll have my book to help me if I get stuck. And I'll see you on Monday. Oh, don't say that, because I'm not having any time stamp to this thing. Stop recording. That's not the right mouse. Goodbye.